Hello, my name is Dmitry and welcome to the DPLABS channel. Today I'm going to tell you about how a heat pump works. For example, right now we're installing and setting up a heat pump and you'll see it. We'll explain the operating principle and we're about to fill and configure it. This heat pump serves a small hotel, or rather a small dormitory for workers built from sandwich panels, about 220 square meters. Here, there's a small boiler room like this. In this boiler room, there are two hot water tanks, which are heated by the same heat pump. Here is the heat pump itself. Right now, it's without the cover, without the casing, but we'll install the casing soon. And other systems, a water purification system, a very interesting ceiling cooling and heating system. In summer, it cools through a heat exchanger, and in winter, it can be heated. It also takes into account ventilation heating. For this heat pump, the source of low potential energy is water from a well, which is always at 7 to 8 degrees Celsius. As it passes through the heat pump, it cools down to 4 degrees and is then discharged either into a pond, there's a pond not far from here, or we're testing how it will work if we discharge it into an overflow well located at the other end of the property. Will it silt up or not? We'll find out. I think everything will be fine. The well here is in limestone and its absorbency is quite good. So for the hot side, we use direct condensation into the floor. Now I'll explain how this is done. Look, two pipes run from the heat pump to the condenser. Here they are, supply and return. Here they go running along. Later, all of this will be insulated. It goes over here, I'll show you later, and heads to the manifold. And the return pipe also passes through a heat exchanger like this one. It's for heating the ventilation and the ceiling. This allows us to lower the condensation temperature. The lower it is, the higher the efficiency will be. Yes, I wanted to mention that a heat pump works on the following principle. It cools a low potential energy source, and by doing so, it extracts energy from it. That is, it operates based on a phase transition. In the evaporator, the refrigerant, after the expansion valve, expands and cools down, for example, to 0 degrees, and then this heat source at plus 7 degrees heats it up. It gets superheated, enters the compressor compresses it, and as the gas is compressed, it heats up, raising the temperature to somewhere around 70 degrees. As a result, excess energy is released. In this mode, for every kilowatt of electrical energy consumed, with low condensation at around 30 degrees, you get 5 kilowatts of heat, which is very efficient. Let me show you where all of this goes next. Here, finishing work is still underway, and this is how the heating system is set up. It comes to the manifold, which has solenoid valves. There are also check valves here, and this pipe transitions into a galvanized steel pipe, because using copper would be very expensive. There are about 2 kilometers of this pipe running under the floor everywhere here. And basically, each room here has its own circuit so that people can control the temperature themselves. These valves, well, the solenoid valves, close, and as a result, the heating stops flowing. We've heated it up a lot here. It's really hot right now. Also, in every room, there's a cooling ceiling which can either heat or cool. For a room of this size, there will be ventilation and so on. Actually, the pigeon was stolen somewhere, so you get direct condensation. Why was this done? We do not require a water circuit nor circulation pumps, and furthermore, there is absolutely no loss during the heat exchange process, specifically 5 degrees Kelvin. That is, we can keep the condensation temperature about 5 degrees lower. As described, there will be a link to a video about the theory of how heat pumps work. The link is to a Soviet video from around 1985 or 1987. I really liked it. The explanation is very clear and accessible. Check it out if you're interested. Heat pump. So let's come closer and take a look. Here it is, for now without the casing. The casing is over there. So, what are its main components? Oh, right. The compressor. Here we have a Toshiba rotary compressor, a rotary type with inverter control. The heat exchanger, the coil, the DHW, domestic hot water heat exchanger. In other words, first the hot gas passes through the DHW heat exchanger. It's always directly connected to it. And if you need to heat water, this circulation pump turns on and circulates water through the DHW tank. Right now, the DHW is being heated by superheated steam. It has been heated up to 62 degrees, which is more than enough for the floor heating. So next, over there, go around to that side, you'll see a small square unit, and that's the plate heat exchanger for the cold circuit. On one side, water from the well passes through it, and on the other side, refrigerant flows in countercurrent. There's also an electronic expansion valve. You just can't see it from here. It's controlled by a servo drive. This here is our sight glass. Look, the circuit hasn't dried out yet. There's a little bit of yellow here. And here is the sight glass and the shutoff valve. This is our controller for the heat pump. This is the inverter, which we made ourselves. It's potted together with the capacitor. What's interesting is how we solved the inverter cooling issues. Part of the cold gas after the expansion valve passes through this heat exchanger. This was just an aluminum profile with channels. It goes back and forth through it, and by cooling the inverter this way, it never heats up above 20 degrees at all. I don't even know how it heats up because the sensor installed inside the IGBT module shows a minimum of 27 degrees. That's what it always shows. Right now the circuit isn't fully charged. There's not enough refrigerant. We're going to add refrigerant now and check to make sure the parameters are correct. We have a special station, a manometric test. I like how it's connected. Now we'll adjust it so that we have the correct condensation and evaporation temperatures. And why do we use an inverter compressor? Since our load is variable, some parts of the room may be closed, others open. The compressor needs to reduce its speed so it doesn't max out. We control the compressor speed and then by the temperature of the return line in the refrigerant circuit. We set it to about 30 degrees and that's fine. That's how everything works. Many people claim that heating with a heat pump is not cost effective because of its high price. And supposedly its efficiency isn't that great. But the issue here isn't even about the price. In our country, no more than 15 kilowatts of three-phase electricity is allocated for a household for free. And if you want more, you have to buy additional capacity. That's quite a big problem. Just imagine, you don't have gas, nothing, you don't want to heat with a stove, and let's say you have a 200 square meter house. No matter how you look at it, even with good insulation, in severe frosts, you'll need about 12 kilowatts of electricity. And besides that, you also have other needs, etc. And sometimes you have to install a heat pump simply because even if you have the money and are willing to pay for electricity, you just don't have enough power available. Here, the heat pump saves the day because it only needs a quarter of all that. As for the price, half the cost of a classic heat pump with a geothermal loop is the work for drilling the loop and its piping. This is when HDPE pipes are buried in the ground. Basically, no matter what anyone says, you can't get more than 30 to 35 watts per meter from the ground. Some part of the loop will eventually freeze through. A meter of drilling costs at least 1,000 rubles. Here, we use something a bit cheaper. In our Domodelsky district, you can get a very good yield from a well. I've even gotten 20 cubic meters from a single well. The aquifer is very water rich, made of limestone. The pump is installed, it doesn't consume much. A deep well with a 25 millimeter diameter pumps out water and circulates it through the system. Such a heat pump costs around 400,000 rubles. You can assemble it yourself. If you, gentlemen, are interested, when we assemble the next heat pump experimentally, I can show the assembly process, explain what's what, where to buy things, and how much it costs. Because there really aren't any major problems with this. The heat pump runs on R410 refrigerant. It has gotten more expensive now, about 10 to 11,000 rubles per cylinder. A lot of refrigerant had to be pumped into this circuit because of the large condenser, about 40 kilograms. We tightened special springs. Alright, yes, I'll blow it out now. We need to blow out this monolithic system. We adjusted the refrigerant a lot. It's fine, there's no air left in there. Turn it over. This is how it's filled through the liquid phase. Alright, now I'll try to fill it first without turning on the compressor. This is what a monolithic station looks like. Here we can see the low pressure and the high side pressure. Opening it up. There it goes. Yes, it's flowing slowly. There the drama has started. But we probably won't be able to fill it this way. We'll have to turn on the compressor. Yeah. It's not flowing. Right now it's 100 grams. I think now we'll need to put in about 2 kilograms probably. that leaked out, damn it, this one. Part of it, because damn, with these unused hoses, that stuff will just get thrown out. The hose is a pain in the ass, damn it. Now, we're going to carefully add refrigerant to the running machines in small controlled doses until we clearly see gas subcooling and the superheat is well within its normal operating range. And the evaporation temperature is within normal range. Well, I'll just unscrew it and add it. Right now, it's working just a little from the canister. So we can monitor the T1 reading. When charging through the liquid phase, you have to be careful not to flood the compressor, otherwise you could get a hydraulic shock. It's not as dangerous for a rotary compressor, but still. Alright, we've charged 2 kilograms. Let's see what's happening now. So according to the readings here, look, our evaporation is at 0 degrees. Condensation is at 18, it will stabilize soon. Alright, we are observing the superheat. We have 4 kilograms and there is currently no subcooling present yet. We need to add more refrigerant so that the condenser gets a bit flooded and we get subcooling. Right now it's at 6. Now the TXV will react to the increase in subcooling and let more refrigerant through. Here you can take a look right here. This is how the TXV works. The electronic one is trying to regulate. It's trying to maintain a superheat of 4, but it needs to stabilize. It will gradually get there. Now we'll add another kilogram, turn it up to maximum speed and adjust accordingly. Or better yet, 2. Well, look, gentlemen, now we have subcooling. Here, take a look right here. 2.4 kilograms. Basically, that's fine. That means there's enough refrigerant. This is a subtle point. If you overfill it, the discharge temperature will spike, the compressor will struggle, and things won't work properly. Now let's let it run for a bit and see how the parameters settle. Alright, that's it. Let's crank it up all the way. So gentlemen, the system has stabilized. We have 5 degrees of superheat and 2.2 of subcooling. And just so you understand what superheat is, there's a relationship between the pressure of the refrigerant and its temperature. It's a constant. So in this case, we look at the fact that we have a certain refrigerant pressure, let's say roughly 7.52 bar on the suction side. At the same time, there should be a certain temperature. Let's say, according to the boiling point, it's 1.5 degrees Celsius. But in our case, it's higher by 6 degrees. Those 6 degrees are what we call superheat. It's like a superheated liquid, but still... Yeah. So basically, this means the refrigerant is in a superheated state. And subcooling is when the temperature of the refrigerant at the condenser outlet should be at a certain value, but it's actually colder by a certain range. That's how it works. We've achieved these parameters. Now we're switching to maximum speed. All right, we need to do it this way. Let's set it so the temperature is higher. Otherwise, it's running at minimum right now. Set the target higher, and it will start ramping up the compressor. It's going to get really loud now, but that's okay. Right now, it was running at 30 revolutions per second. Now it'll go up to 90 revolutions per second. And that's about 5,500 RPM, something like that. Now it's like... I wanted to talk about the power consumption. So the compressor, the heat pump is running at full power. Right now it's producing about 27 to 30 kilowatts of heat. because the condensation is low and the COP is really good. And it's consuming 5.2 kilowatts across all phases. There you go. So that's actually pretty good. So what do we have there? Legion has entered. Well, indeed, my Loriba. Yeah, and I really don't want to leave this important manometric station because in the general slag everyone can easily mess with it and quietly tinker around with the settings and adjustments. Alright, go ahead. Go on. Go on. Come on, damn it. Yeah, I'm tightening it. No? Tighten it. There you go. Something's not right. Tighten it. I'm tightening it. The hose is freezing. Tighten it. What's going on? Hello there. Again. Did they mess everything up because of the bend or something? What's going on? I can't do this anymore. They couldn't have broken all of them, could they? Huh? Bro, what do you think? Oh, damn. I pushed the cylinder the wrong way, and now I'm going to burn myself on the neural switch. Hold on. Yeah, just hold on. Yeah, now it's dropping below 0. Yeah, it's supposed to count as a negative.